Alrighty, guys. Good afternoon. Welcome back to MAC1140 pre-calculus. Today we're going to talk about functions, and I know this is something that you've definitely encountered in algebra classes of yore, but we're going to look at them a little bit deeper and a little bit more of a sophisticated perspective than maybe you started with. What we're doing today is kind of a foundation for the rest of the course, so it's super duper important that we actually learn this stuff. I want to apologize. This thing, it's converting, and the computer, my work computer here is a little bit noisy. If you have any trouble hearing me due to the fan noise, please just say something, and I will either stop the conversion or type in chat. But yeah, let's do it. MAC1140, section 009, which is a pre-calculus class. And today is the 31st of August, 2021. Today we're going to talk about functions, which is section 2.1, and their graphs. Which is section 2.2. It feels a little bit dry, but we have to begin with a definition. So a function is a rule comparing inputs with outputs. And that's a good intuitive way to think of a function, but there's also a little extra stipulation with the restriction that each input is paired with one and only one output. And one of my goals today is to try and convince you why this last part is important. Why the idea that each input goes to one and only one output is kind of a big deal. There are more general input-output pairing rules. Like if you eliminate the second part of the sentence and you just take this to be your definition, then the type of thing you're talking about there is what's called a relation. So every function is a relation, but not every relation is a function. There's a bunch of ways we describe these. What I'm going to draw for you here is called a mapping diagram. So what I have on the left over here is kind of an abstract set. Just think of everything in the bubble as being a set. Maybe they're numbers, maybe they're houses, maybe they're cars. And then over here, I'll have another sort of abstract set. Could be anything. And the idea is that the function takes each element from the first set and sends it to one and only one element in the second set. And the function itself is f. So I think we get used to this idea in other algebra classes that f of x is the function. That's really not correct. F is the function. X is the input, and f of x is the particular output associated with the input x. All of the stuff on the left over here, these are all of the inputs, and these are all of the outputs. The set of all inputs is called the domain, and the set of all possible outputs is called the codomain. If you just restrict to the actual outputs themselves, that's called the range. So finding domains and ranges, we've talked about how to find domains. To find the range of a function, usually you're going to want to look at its graph, and we'll talk about that a little bit. So there's a bunch of different ways I can describe a function. I know one you're certainly familiar with, so I want to begin with that just to kind of get comfy with the notation. So again, the notation f is the function. X is like an arbitrary input. And f of x is the output from f when fed the input x. And probably the most common way of describing a function is to give you some sort of like algebra formula that tells you how to get the output from a given input. And that's where this f of x notation becomes so pervasive. But these are the basics. If I want to refer to the function itself, remember that is the rule, not any particular input-output pair, but the rule that tells you how to get an output from an input. X is just an arbitrary input, and f of x is the specific output you get when you feed f the input x. So this notation right here is not multiplication. This is not f times x, even though they are concatenated, like written next to each other. This is definitely not multiplication. You can think of f as like a hungry dude. The parentheses are like his mouth, and you feed him this x, and he poops out something else, namely f of x, the output. There's one other kind of nice diagram that I want to show you here. So this is called a mapping diagram. And it's a useful way to visualize functions sometimes, especially when we talk about things like function composition. The other kind of nice way of visualizing these things are what are called machine diagrams. And they're very similar. The machine diagram, we're basically thinking of F as being like a machine on an assembly line. In a big factory, you have these machines. Maybe empty soda bottles go in and filled soda bottles come out. So I can think of the F machine as something that takes in X's and spits out F of X's. And I could connect this machine to other machines. And that'll be a useful metaphor for us down the road. But yeah, these are the basics, and I'm sure this is at least somewhat familiar to everybody. Let's look at some particular things we can fiddle with.
Mr. File Sticker, your connection is not working well. I don't know if you can see the chats.
Oh, let me see here. Oh, thank you for the heads up.
Yes, sir. I didn't want you. It does seem better. You're clearer now, but for a second you just froze for a good 20 seconds.
That's strange. Okay, did we miss anything back here? I'll just hold.
I believe you started freezing like after the machine diagram thing, kind of.
Okay. Okay, so we're all comfy with the mapping diagram and this notation. The machine diagram is just another way of describing the same sort of thing. So we think of F as like a machine on an assembly line. Shit comes in, gets messed around by the machine, who knows, could do anything, and then it sends something else out. And every one thing that comes in corresponds to one thing that goes out. The nice thing about the machine diagram is you can think of this as being one of many machines, possibly connected to each other. And that'll be a useful metaphor for us down the road when we talk about combining functions. I do think the right thing to do here is to look at a couple specific examples and try to just get you really comfy with function notation. So one of the things I have to do in this class, because the next class is Calc 1, I have to kind of gatekeep function notation. Meaning I can't let you through this class unless you learn what function notation means and how to use it. To that end, I'd like to do something like this. So let's compute f of 0, f of 1/2, f of -3, f of a squared, f of 1 over x, and f of a plus h, where f is the function defined by the rule f of x equals x over x squared plus 1. So the objective here is just to kind of understand what each of these things means, right? To understand it in the context of this particular function, and then to understand how to get these sort of things from any other function for which you have a nice formula. Oh my God. Oh, just like drank the very last of this cold brew coffee. Lots of grounds. Okay, let's start with the gentler stuff like f of 0. F of 0, f of anything is what you get by taking this formula and replacing x by that thing, and you want to do so in parentheses. I'll show you what I mean. So f of 0 would be parentheses 0 divided by parentheses 0 squared plus 1. And I know what you're thinking, these parens might be a little bit redundant. Right? Do I really need to write them? The answer is, well, for plugging in 0, no, I guess you don't. But when it comes to more complicated shit like this, you really do. So get in the habit. That's what I'm saying. We want to start building good habits that will help us in calculus. Here is the first and most important. When you plug into a function, always do so in parentheses. So the top is just 0. And downstairs, 0 squared is still 0. 0 plus 1 is 1. So this is 0 over 1, which is 0. So the input 0 gets mapped by the function f to the output 0. We get some practice with fractions here. F of 1/2. Okay. This time you really do want those parentheses. That's parentheses 1/2 divided by parentheses 1/2 squared plus 1. And I'm even going to add some more in a second. Because remember, big fraction bars like these always imply parens top and bottom. And that's going to be important when we simplify this at the end. But before we do that, I need to clean up that downstairs. So 1/2 squared is 1/2 times 1/2, which is 1/4. So downstairs, I'm going to write this as big parens 1/4 plus 1, like that. And I'm putting the whole bottom in parentheses to remind myself that, okay, yeah, this is a fraction made up of fractions. The top is a fraction, the bottom is going to be a fraction, but I need to remember kind of what's the big fraction and what are the little fractions inside. So my numerator is 1/2 and my denominator is this whole thing. So that is 1/2 divided by, now, if I'm going to add 1/4 to 1, I need to think of this 1 as 4 over 4. And then 1 over 4 plus 4 over 4 is 5 over 4. And I want to say, again, without the parentheses, this is an ambiguous statement. If you just had 1 division bar 2, division bar 5, division bar 4, it's not clear whether that's 1 being divided by 2 divided by 5 divided by 4, or some other permutation of parentheticals. So the big fraction bar and the implied parentheses top and bottom tell us exactly what to do here. The numerator, the big numerator, is 1/2, so I'll leave him alone. And the denominator, the big denominator, is 5 over 4. So I'm going to flip this guy and multiply him by this guy. So that's 1/2 times, I flip this over, 4 over 5. 4 is 2 times 2. And you can cancel one of the 2's downstairs there. So this is going to be 2/5. Or you could write it as 4/10 and then divide top and bottom by 2. Any questions about the arithmetic there? I have a dirty secret. I don't know if I've told you guys this, I forget. I didn't really understand how to manipulate fractions until Calc 1, right? Like I would run into things like this from time to time, and because I didn't quite get that division isn't associative, right? Not only is it not commutative, it's not associative. I would from time to time run into trouble trying to simplify things like this, or something like 1 divided by 5 divided by 4. And the trick is to kind of identify your big fraction and put the top and bottom in parens. Okay, so if you ever have trouble with something like this, or you ever feel like something like this is unclear or needs a little bit more justification, don't be shy, right? Better to get that sorted out now than to wait until Calc 1 like I did and really struggle with it. F of -3. Here's another place where those parentheses are going to be really important. So this is -3 divided by parentheses -3 squared plus 1. So this time it's the parentheses downstairs here that's super important. A quick note. If you write -3 squared like this is ambiguous. Is that the negative of 3 all squared like this, which would be +9, or the negative of 3 squared like this, which would be -9. So when you go plugging in a function, please always put the input in parentheses. It might seem silly, but I promise you, it will save you at least 1 point on an exam somewhere, probably more. So the top is -3. And the downstairs is the square of -3 plus 1. So -3 squared, that's +9. So that's 9 plus 1 downstairs. And that means this is -3/10. You see what a big difference that would make. If I just wrote this down here, we're either going to get -3/10 out, or we're going to get +3/8 out. And that's a pretty big difference. All right, next up would be f of a squared. I could ask you for f of anything. I could ask you for f of a soccer ball or f of dog shit. F of whatever you want is what you get by coming in here and swapping these in parentheses for whatever you're going to put in here. So f of a squared. So what? I don't know what a is. It doesn't matter. I just follow the same pattern. Everywhere there's an x in this formula, I'm going to replace it with parentheses a squared. So I get a squared over a squared squared plus 1. All right, we're learning to work in the abstract. It doesn't matter that I don't know what number a is. I can still do this computation. The top, a squared, it's just a squared, nothing fancy there. Downstairs here, now we can use one of those rules for exponents that we talked about last week. I've got a raised to a power, and then that's all raised to another power. So I'm going to multiply those powers. So it's going to be a to the 4 plus 1 is plus 1. There's nothing we can really do with that. Can I cancel the a squared into this a to the 4? Write it as 1 over a squared plus 1?
No, you can't.
Very good, Suzanne. Why not?
If it was like a to the 4th plus like a squared, then you could, because they both share the same factor.
Good. So we cannot cancel like this because a squared is not a factor of the bottom. Downstairs. All right, so you can only cancel common factors. If you're wondering, can I cancel this? Can I not cancel this? The thing you need to ask yourself is, can I factor out that thing I want to cancel? So the a to the 4, that has a factor of a squared, but 1, that does not have a factor of a squared. So unless your immediate step before was factoring, you can't cancel. So this really is simplified. This is as good as it's going to get. All right, these last two are where all the fun stuff is. F of 1 over x. Well, that means anywhere there's an x in the original formula, I'm going to write 1 over x instead, and again in parentheses. So it's 1 over x divided by 1 over x squared plus 1. And drawing the fraction bar nice and long here helps us remember those implied parentheses. The numerator I'll leave is 1 over x. The downstairs I can clean up quite a bit. 1 over x all squared, well, just like 1/2 squared is 1/4, this is going to be 1 over x squared. Right? It's 1 over x times 1 over x, which is 1 over x times x, or x squared. And then the plus 1 is just a plus 1. And I put my big parens to remind myself to handle this and this as separate quantities. I can have a common denominator downstairs here. That common denominator would be x squared. So I think of 1 as x squared over x squared. And I see that this is 1 plus x squared over x squared. And now again, I've got a big fraction where the top and bottom are each little fractions. So I'll leave the top alone. And I flip and multiply by the bottom. Can I cancel anything here? Let me continue this over here.
Can you cancel an x from both sides?
Yeah, there's a factor of x top and bottom that I can cancel. It's not coming from the 1 plus x squared. It's this x and one of these x's. Right? If I write that as a single fraction, that's x squared over x times 1 plus x squared. So there's 2 x's multiplying each other upstairs. There's one factor of x downstairs. If you cancel one of those, you get x over 1 plus x squared. And fun fact, you'll notice this is the same as the original, isn't it? X over x squared plus 1, x over 1 plus x squared. That means that this function somehow interacts with the other function 1 over x in a neat way. And we'll talk about that when we talk about inverses. Okay. One more, right? F of a plus h. We're going to work a lot in this class with something called a difference quotient. And f of a plus h is a portion of that difference quotient. Before I get into this, and please don't write this part down, just think along with me. I want to ask you some sort of qualitative questions about f of a plus h. Is this the same as f of a plus h? Is this the same as f of a plus f of h? Or is it something else entirely? All right. So you don't need to write this down, just think along with me. F of a plus h, is that the same as f of a plus h, like this? Do I just write a plus h at the end of that? You can help me out. Is this a true statement?
No.
Yeah, no, it is not. It is not a true statement. These are very different animals. You're kind of adding an h on the outside here, we're adding an h on the inside here. Okay, what about the second one? Here the h is on the inside of the function f, just like over here. Is this equal to this?
No.
Again, no. There are some functions for which this is true. Those are a special family of linear functions, but in general, definitely no. So f of a plus h is something else. What is that something else? Well, I'm going to take my formula for f, and everywhere there's an x, I'm going to write parentheses a plus h. So that's friends a plus h over friends a plus h squared plus 1. And just like in the previous guy, I can't cancel the a plus h's. There is a factor of a plus h in the top, right? The top is just this times 1, but there is not a factor of a plus h downstairs, right? This 1 doesn't have an a plus h that I could factor out to cancel with that. So no cancellation can occur here. There's really not much we can do. If you want, you could multiply out the bottom. That's a squared plus 2ah plus h squared plus 1, because a plus h quantity squared is a plus h times a plus h, which you can FOIL out as a squared plus ah plus ha plus h squared, which is squared plus 2ah. Now, whether you want to actually do that, whether this is somehow more useful than this, depends on the context you're working in. So sometimes I would say, you want to leave it like this. Sometimes you might want to leave it like this. It really all depends on the problem that you're looking at. Most of the time, I would say probably just leave it like this. All right. Again, this sort of stuff, especially these last few sort of things, these are really important. You got to get used to what function notation means. F of a plus h is what we're looking at here. This is not f times a plus h. Even though this kind of looks like multiplication, where you've got the two things concatenated sitting next to each other, it's not multiplication. And specifically, say, this is not the same as f of a plus h, nor is it the same as f of a plus f of h. There is no such arithmetic or algebra that you can do with this. You just have to plug that into the function. That's the only way of figuring out what that thing is. You'd be amazed how often I see this mistake. So, any questions about any of these pieces? I see some stuff in the chat there. Oh, I see. All right, very good. Just canceling the common factor of 2. All right, so I'll say it one more time. You got to get comfy with function notation. You must. And I'll give you some justifications for the use of that notation after we talk about graphs a little bit. Before we talk about graphs, there are other ways of describing functions. So the way we just saw, where you have an algebra formula for the output as it depends on the input, that's great. It's a super useful way of describing functions, and that's 9 times out of 10 what we're going to do. But there will be some instances where I want to describe a function in a different fashion.
Whenever you're done writing, your screen is out of focus for some reason. I don't know if it'll go back in focus.
It should, but let's see. Try to force it in. There we go. And,
Beautiful.
all right. So some different ways we can describe functions. The first we just saw is algebraically. This is where you have like f of x equals and then some algebra formula. involving variable x. This works fine, and it's what we'll use most of the time. But there are some cases, like when we start to learn about inverse functions, algebraically, lost an L. Sometimes I'll want to describe a function slightly differently. One of those useful ways is verbally. Right? So I could say, you know, f of x is the function that takes x, multiplies by 3, subtracts 1, then takes the square root of all that. Right, this is one example of a function being described verbally. A reason for doing this, we will see when we go to talk about inverse functions. Those are functions that kind of exactly undo some other function. The most naive and simple way to get an inverse function is to describe the original function verbally, and then figure out how to undo each of those steps in reverse order. The algebra behind it can be a little bit wonky, but going through the process using language is surprisingly simple. So as long as you can go back and forth from an algebra formula to a verbal description, you'll be able to find inverse functions without doing any algebra, and then just write down the answer. It's really cool. There are other reasons why we want to do this too. And then translating back and forth is an important skill. So if I wanted to take this verbal description here and write it as an algebraic description, I would say f of x is equal to, what does this thing do? It takes the input x, multiplies by 3. Okay, that's 3x. Then subtracts 1. Okay, so we're going to take 3x and then subtract 1. And finally takes the square root of that. So that's this whole thing under a ref. So going back and forth between these two is a useful skill. Another way we can describe a function is by giving you a chart or a table. You know, just input-output pairs listed explicitly. This is actually kind of boring because if I've got some table of input-output pairs, then necessarily there's a finite number of inputs on that table, right? Your table can't go on and on and on forever. And we've seen in this class that, you know, between any two real numbers, there's infinitely many other real numbers. The vast majority of the functions we're going to consider have infinite domains, right? Even if your domain is just a small interval, like from 0 to 1, there's infinitely many numbers in there. So you won't be able to get all the information for your function down in a table with only finitely many columns or rows. So this shit's kind of boring. But there is one non-boring way to describe a function we haven't talked about, and that's graphically. So this is the graph of a function. I might as well just define it for you. The graph of a function carries all the information for that function. So the graph of a function f is the set in the xy plane. So it's going to be a bunch of ordered pairs of the form x comma f of x, where x runs over the domain of the function f. Right, so it's all ordered pairs of the form input comma output. The y value on any point on the graph is the output associated with the input, that is the x coordinate. And if you have the whole graph or enough information to infer about the whole graph, then you actually have a complete description of the function every bit as good as the algebra formula. So these are all equivalent, except for maybe this guy, which is, necessarily finite and requires some interpolation. Okay. Before I get into practicing with graphing functions, let me just show you sort of your homework setup for this week. So you have a new homework set that's out. It released today, and it is due at the start of class on Thursday. Here's that homework. The first few things are very, very simple, just evaluating functions, and then the sort of stuff that we did at the very start here, like I give you some formula and then ask you to compute these sort of things. Practice these, make sure you're really comfortable, especially with the stuff like this towards the bottom. Like I said, skills with function notation is something I absolutely must gatekeep as a part of just being a math professor. There's going to be quite a bit of piecewise function work in here. So the next thing we're going to talk about is piecewise functions. And then the remainder of it is all graphing. So let's discuss piecewise functions. The reason I'm not including piecewise functions as a separate thing here is because they're actually a subset of algebraically defined functions. Or you could define them verbally too, but generally a piecewise function is given algebraically. So what is a piecewise function? These are functions where the rule for pairing outputs is different for different inputs. That's all. So a piecewise function is a function where I've got maybe 2 or 3 different rules for specifying an output. And if x comes from, some set, then we're going to use this rule. If x comes from this other set, we're going to use this different rule. And you could have many different pieces. But sort of the general way you'll see these things written is f of x equals, and then an open curly brace, kind of like the set notation we saw on day 1. And there will be one rule or formula here, and then some specified range of x values here. And often the word if is in between them. So we'll say f of x is equal to this rule or formula if x comes from this range of x values. And then there could be others. Another rule or formula down here. And then, it says, okay, we're going to use that rule or formula if x comes from this range of x values. And you could have like 3 different rules. You could have 10 different rules if you want. But these are what piecewise functions are. And I guarantee you there's at least 1 or 2 of these that you've bumped into in the past. Specifically the absolute value function. So you all saw this on the first homework. I think it was like 15C or something like that, where you were looking at the square root of a squared, or like square root of 16a squared, something like that. And I asked you, is this equal to a, or is this equal to 4a? The answer there is no. It's actually equal to an absolute value of a, or 4 times the absolute value of a. And that's coming from the way squares and square roots interact. But the absolute value function is best defined piecewise. So you think about, what does absolute value do? The absolute value of x depends on what's going on, right? It leaves x alone if x is non-negative, right? If x is positive or 0, then the absolute value of x leaves it alone, or it turns x positive if x is negative. Okay. If I just say it like this, though, right? If x is a non-negative number, absolute value just leaves it alone. And if x is negative, it's made positive. But this is not something you can do algebra with, right? Like, you're not about to plug these words into any equations and start solving them. It's not a very useful definition if your goal is to solve an equation or manipulate an expression. A far more useful way of writing this is as the piecewise expression. The absolute value of x is just x if x is non-negative, meaning greater than or equal to 0. And if x is less than 0, then the absolute value should turn it positive. Well, how do you take a negative number and turn it positive? What algebra operation will take a negative number and make it positive?
Multiply by 2 or by itself.
Not multiply by 2. It's true that if you multiply by
The
itself,
power.
that will make it positive. That's true, but it will also change the size, right? So I don't want to square it. It's true that squaring a negative will make it positive, but there's a simpler operation, one that doesn't alter its size.
Multiply and by -1.
Very good. Multiply by -1. That will turn the negative positive, and it will also preserve the size. So this is your definition of absolute value. In this class and in calculus classes, you should take this as the definition of absolute value. It's also the best way to get the graph. So normally, if I want to graph a function, I don't know anything at all about it, I can just make a table, right? I can make a table of inputs and outputs and then plot those in the plane. I want to show you how to be a little bit more sophisticated about graphing piecewise functions, and we're going to start with the absolute value here. Graphing piecewise functions. I am assuming that everybody here, if I gave you just an arbitrary function, could make a table, right? An XY table and plot those points. That's not exciting. One of the big goals for us in this class is to get to a place where we can graph most functions quickly, based on pieces that we know, geometry, stuff like that. So we're going to start our first example here, just sketch the graph y equals the absolute value of x. And we're going to remember that the absolute value of x is a function that is defined piecewise. I'm going to write it like this: negative x if x is less than 0, and positive x if x is greater than or equal to 0. Just switching the rows. All right, how do you do this? How do you graph a piecewise function? Well, you start by graphing each of the pieces. So I'm going to start by sketching two graphs. One of them is y equals negative x. The other one is the other piece, y equals positive x. Neither of these have to be perfect works of art, just good enough to give you a feel. Okay. Y equals negative x. This is a line with slope -1 and y-intercept 0. This is a line passing through the origin, slope -1. That looks like this. We're looking for some specific points. 1, comma, -1 is definitely on this graph. -1, comma, +1 is definitely on this graph. These things we can say for sure. 0, 0 is definitely on this graph. Right? If you made a table for y equals negative x, you could very quickly get this line. Similarly, y equals positive x is a line through the origin with slope +1. So again, 0, 0 is on there. 1, comma, 1 is on there. -1, comma, -1 is on there. So to graph a piecewise function, first, you just graph each of the pieces as its own thing. Then, with each one of those graphs, you identify the portion of the graph that matches the specified x values. So if x is less than 0, what part of the graph am I looking at here? Well, here's the x-axis. This is x equals 1, x equals 2. This is x equals -1, -2, and so on. X is less than 0 means I'm looking at this stuff, not including that point at the origin, right? We would put a parentheses here because it's a strict inequality. So that means I'm the corresponding part of the graph is this part, not including the point at the origin. On the other hand, if I look at the graph of my second piece and I restrict my attention to the x's which are greater than or equal to 0, that means I'm looking at these x values, including 0 and anything to the right. And the corresponding part of the graph is this part. This would include that point at 0, 0. And this is how it's done in general, not just for the absolute value function, but for any piecewise function. Graph the pieces on their own, then identify the part of the graph that corresponds to the range of x values in your piecewise definition. So this function is equal to x, but only if x is greater than or equal to 0. Okay, I want to take the graph y equals x and find the part of that graph that has x values which are greater than or equal to 0. That's exactly this. And the same thing over here. I take my graph y equals -x, and I identify the part of it that has x's which are less than 0. That means x's which are over here, which means we're talking about this part of the graph. Then what you do, you take this piece and you overlay them. You set them on top of each other. And that is the graph of your piecewise function. So the graph y equals absolute value x is this piece here and this piece here. And the point at the origin is coming from this piece, not from this piece. That's it. There's your graph. All right, nothing too crazy. Let's get a little practice with something slightly more complicated, and then I'm going to show you one really weird piecewise function. But first, I just want to make sure that we're genuinely comfortable with kind of this procedure. there any questions about what we were doing here, or why we were doing it, or where anything came from, or how we used it to get this? Okay. All right, how about something a little more exciting? Well, tell you what, let me do a few more examples here, because I have something slightly gentler. So let's sketch the graph of a function. I'm going to call it h of x. And this is kind of a weird one, but not too weird. It's equal to 0 if x is less than 0, and it's equal to 1 if x is greater than or equal to 0. So again, I'm going to start with a graph of the pieces. The pieces here are y equals 0 and y equals 1. Okay. The line y equals 0 is a horizontal line going through the origin, right? Every x gets sent to 0. So this one is a little hard to see. I guess I'll just embolden this. That's y equals 0. Just a horizontal line going through the origin. The graph y equals 1 is also a horizontal line, but this one doesn't go through the origin. This one is up here. Every x just gets sent to 1. All right, so there are my pieces. Next, I want to identify the part of the graph that matches with each piece's restriction. So if x is less than 0, which part of the y equals 0 graph am I talking about? Well, that's just like before. That's anything to the left of the origin. That's this stuff. And that happens to sit right on top of the part of the graph we're going to keep. And for the other guy, if x is greater than or equal to 0, that means I'm talking about this stuff. So in other words, I'm looking at this portion. Okay. And then like we did before, I'm just going to overlay them. I'm going to take this part of the first graph, an open circle here, and this part of the second graph with a filled in circle here, and I just set them on top of each other. All right, that's it. That's the graph of this function. This is, of course, the x-axis, and this is the graph y equals h of x. So something weird is going on at 0. Obviously, this is kind of a strange graph. These pieces don't like match up. The name of this function is called the Heaviside step function. So you can see why it's called a step function, right? This is kind of like a stair. We're walking, 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 and then we take a big step up, and then we're walking, walking, walking. This is a really important function in signal processing, differential equations, electrical engineering in general. Basically, you imagine that the x values are measuring time, and you have like a battery or a switch or something, and the battery is off until time t equals 0 when you flip the switch, and then the battery is on. Right? There's something kind of very binary about this. It's also a useful input in differential equations. If you're talking about a system where, a physical system where, maybe nothing is happening, and then all of a sudden you start pushing on something with force 1, and you continue to push with force 1. It's a very useful function for a lot of different engineering applications. Oliver Heaviside is the man after whom it's named. And later in the course, when we talk about partial fractions, he's going to show up again. All right, any questions about where we get that black graph from? Okay. Let's do one more like this. This time I am going to assume something about you. I'm going to assume that you remember a few basic graphs from high school or college algebra or wherever. I'm going to define my function piecewise to be x squared if x is less than positive 1. And let's make it 3 minus x if x is greater than or equal to 1. So again, sketch two graphs to start. Y equals x squared and y equals 3 minus x. Y equals x squared, you probably remember, is a parabola. Vertex at the origin, lots of points on this. Like 2, 4, 1, 1, negative 1, 1, negative 2, 4, all that good stuff, right? And of course, the origin itself. 3 minus x is a line. The slope of that line is negative 1. The y-intercept of that line is positive 3. So we'll go 1, 2, 3 up. And then our slope. Over 1, down 1, 1, down 1, and so on. So here's 3 minus x. Now for each one, I figure out which portion of the graph I'm going to keep. So from the x squared graph, I only want to keep the parts where x is strictly less than 1. Here's 1. Everything strictly less than 1 is the stuff over here to the left of 1. Which means I'm going to have an open circle here, and I'm going to take all of this. And on my other graph, I just want the x's which are bigger than or equal to 1. So again, here's 1. Take all the stuff to the right of that, including 1 itself, which means I'm interested in this point and everything to the right of it. So those are my pieces. Then I can put those pieces together into a single graph. Just plotting a few points that I know are in that parabolic portion. Okay, so here's the stuff I get from that first piece. And then the stuff I get from the other piece. We got to think a little bit about the height of this point. If I plug 1 in here, I get 3 minus 1, which is 2. So that means that dot is up here at the point 1, comma 2. And then he looks like this. So this is the graph y equals f of x. It's that piecewise defined function. All right, any questions about where the bottom graph here is coming from? Just for clarification, we will be talking about how to graph quadratic functions in detail a little bit later. We will not be going in detail over how to graph lines. I am assuming you remember lines from high school or college algebra or wherever. If that's not the case, then reach out to me. I'll get you some stuff to work on, some videos you can watch, some problems you can solve to get caught up. Okay, here's my last weird piecewise function. These ones are nice, right? The Heaviside function and this piecewise linear and parabolic function. Both of these are simple examples of piecewise functions. They each have 2 pieces. The pieces are not complicated, and they're both split up over intervals. So like this portion is not terribly hard to figure out. This last example is meant to kind of illustrate the power of piecewise functions and how kind of weird they can be. And so these I would not consider weird examples, but the Dirichlet function is a very weird function. So I'm going to call this one d of x. It's another famous function named after a famous mathematician. Dirichlet. I don't remember Dirichlet's first name. Some people call him Dirichlet, Dirichllet, Dirichlet. If you think of him as a Frenchman, you pronounce it Dirichlet. If you think of him as a German man, you pronounce it Dirichlet. He went back and forth himself. This function only ever takes 2 values. There's only 2 outputs. It's piecewise constant, just like the Heaviside function. Sometimes it's equal to 0, sometimes it's equal to 1. But unlike the Heaviside function, the rule is very strange. It's equal to 0 if x is irrational, meaning x is not an element of the set of rationals. And it's equal to 1 if x is rational, meaning x is an element of the set of rationals. So remember the Q here, this is the set of all rational numbers. And this would be read as x is an element of the rational numbers, just to be clear. This means and that means this would mean x is not rational or irrational. So this is a part of a family of functions called indicator functions. It's 0 all the time unless the input comes from a certain set, and then it dings up to 1. So this function's kind of job is to measure the rational numbers. It spits out a 1 for every rational, spits out a 0 for everything else. This is a case where when we go to sketch the graph, I'm not actually going to sketch the pieces. I mean, I could try to do this like we did before, but these are not intervals, right? The set of irrational numbers is not like the same as x is bigger than 1. It's a really weird set. It's broken up into a bunch of different places, and so is the set of rationals. So here I'm going to do something funny. I'm going to make a table. And just for the record, if you have a function you're trying to graph and you don't know what else to do, make a table. Input, output. And let's put a bunch of shit in here, like -3, -2.5, square root of 3, -1/2, 0, +1/3, +1.5, the square root of 2, 2 itself, and maybe pi. All right. What is d of -3?
One.
Very good. D of -3 is 1. It's got to be either 0 or 1. Those are the only two numbers that this function can spit out. Either 0 if the input is irrational, or 1 if the input is rational. -3 is a rational number, right? Remember what we said on our very first day of class. The integers are contained within the rational numbers. Every integer is a rational. -3 is the same as -3 over 1. That's a fraction made up of whole numbers. So -3 is a rational number, which means d of -3 got to be 1. All right, what about -2.5?
1 again.
How do we know 2.5 is a rational number? First, you're correct. Yes, it's 1. Why?
Because it's not a fraction or under a square root, so it's a real number.
Well, definitely all of these are real numbers. The thing we're trying to figure out is whether it is rational or irrational. And I would say -2.5, it is a fraction. It's -5 over 2. So 5 and 2 are both integers, right? So this is a rational number. Most of the numbers that we think about are rational numbers, right? Anything is decimal expansion is finite n length or repeating. So you could also say that. But yeah, definitely this is equal to 1 because this is a rational number. What is d of -√3? What output goes with this?
0.
0, very good. Square roots are either integers or irrational, right? If a square root is not a perfectly clean number, then it's irrational. What is d of -1/2?
1.
1, good, because that is a rational number. What is d of 0?
1.
Good, very good, 1. 0 is also rational. 1/3,
1.
rational. 1.5?
1.
Square root of
Rational.
2. Yeah, good, good. What about √2?
0.
0, same reason as -√3. 2 is rational, so that's going to be 1. Pi is going to be a 0 again.
0.
Yeah, so this is a strange function. Let's sketch the graph. Let's plot these points at least. So maybe I'll say 1 is way up here. 1, 2, 3, something like that. 1, -2. Okay. This is going to be the graph y equals d of x. And let's just plot these points. So I know I've got -3, 0, -2.5, 0. While I'm here, -2, -1, 0, 1, 2, and 3. Those are all, oh shit, I'm doing this backwards, aren't I? Irrational, shit. All right, I'm sorry. So -3, 1. Sorry about that. You'll see in a second, it's going to be okay. It's not something you need to stress about. -2.5, 1, -2, 1, 1, 1. At all of those rational numbers, we're up here at 1. All right, that's from our table. -3, 1 is on the graph. -2.5, 1 is on the graph. -2, 1 is on the graph. -1.5, 1 is on the graph. -0.5, right? Every nice fraction is going to give me another point up here. And we know there's a shitload of these, right? Like +1/3, +4/5. There's an awful lot up here, but we also know that the line up here is not solid because there are irrational numbers, yeah? Like the square root of 2, that's like 1.4, it's like right here. So here's a point that's down here. Pi. 1 over the square root of 2. Lots and lots of stuff. What do we have? Negative square root of 3. That's like, there's lots and lots of stuff down here also. A fun fact about the real numbers, we said before that between any two real numbers, there's infinitely many other real numbers. You can actually take that statement a little bit further. Between any two real numbers, there are infinitely many rational numbers. And between any two real numbers, there are infinitely many irrational numbers. So kind of, no matter how small you shrink down, no matter how tiny an interval you choose to look at, you're going to find infinitely many points down here and infinitely many points up here. This is a weird function, isn't it? It bounces back and forth, back and forth, back and forth, infinitely fast. And there is no connected piece up here. There is no like little line segment. It's just a faint sprinkling of dust. And then down here, it's a much heavier sprinkling of dust. So it turns out the rational numbers, that is an infinite set. There are infinitely many fractions. So, okay, there's infinitely many points up here. In fact, between 0 and 1, there's infinitely many points up here. But the set of irrational numbers is even bigger. They're both infinite. You might want to think, oh, they're both infinite, same size, just infinite. But no, hold on. There are infinities which are much bigger than other infinities. And the infinity of irrational numbers is one of those infinities that is much bigger than the infinity of rational numbers. So there's an infinite faint sprinkling of dust up here along the line y equals 1. And there's a much heavier sprinkling of dust down here. In fact, this is almost like air. It's almost like it's not there. And this is almost solid. It's almost like there's nothing missing. But of course, there is stuff missing. Every rational number is missing from down here. And every irrational number is missing from up here. So strange function. Piecewise constant, though. Each of the pieces, very simple, right? Y equals 0, that's just a horizontal line down here. Y equals 1, that's just a horizontal line up here. But this time, because of the way we've split it up, the way we split things up here is very complicated. We end up with a pretty complicated graph. This function was used around the turn of the century, the turn of last century, around 1900, to start proving some very strange things about infinite sets and set theory. It led to what was called a foundational crisis in mathematics. Dirichlet was a big part of this, and Dirichlet cuts He was one of the first guys to really try to understand what the real numbers are as a set. What does it mean to say that that line is solid? Very smart man. Shortly after Dirichlet came a man named Gerald Cantor. So d of x is called the indicator function for the rational numbers. Or just simply the Dirichlet function. Another name worth Googling, if this sounds at all interesting to your brain, if your brain tingles when it starts to go, what do you mean different infinities? Another name to look up here is Georg Cantor. One of the great mathematicians of the era, Georg Cantor was hugely unappreciated in his time. Dirichlet was quite famous, and a lot of people liked him because he did a lot of useful things for analysis and quantum physics, stuff like that. Cantor was said, so there's another mathematician, David Hilbert, who put together what are now called Clay Institute problems, math problems that are worth $1 million each. He said of Cantor that Cantor's mathematics is a sickness from which one day the world will recover. That's how much he hated this guy, because this guy started poking all sorts of holes in the logic that was being used by mathematicians of the time. We were just kind of riding on our intuition, and Cantor would, hold up, there are some very real problems with set theory. You can't just start referring to objects and assuming they exist. And it showed that the infinities of the real numbers are different than the infinities of the rationals or the integers. Fascinating dude, very much worth a Google if that sounds interesting to you. But piecewise functions. Piecewise functions, they can be complicated even if their pieces are simple. But most of the piecewise functions we will mess with will be things closer to this. So stuff like this is what you need to get comfy with. Got to get to a place where you can graph these sort of things. Give me just one moment. Alrighty, guys, sorry about that. So yeah, piecewise functions, got to get comfy graphing them. Let me show you something in Canvas really quickly, and then we're going to finish up here. There's not much more to talk about today, but there is one more thing after this. So whether you're graphing piecewise functions or anything else, you need to have a solid foundation. The solid foundation that I'm assuming you guys have, but I'm not foolish enough to actually think everybody has 100% rock solid, are these. So if you go to the course modules, you'll see there's just one thing posted there for now. It's under graphing resources. These are graphs of parent functions in Desmos. This is a Desmos graph that I've saved where you can come in and go, oh, I forget what the graph of x cubed looks like. There it is. Just click right here and that graph will show up or go away. You can toggle it on and off. Or I forget what the graph of x to the 4 looks like. Oh, it looks like x squared, but it's a little flatter on the bottom. Okay. I forget what the graph of the cube root of x looks like. Well, there it is. Or 1 over x squared. There it is. So these are graphs that you guys need to know. When we get to the first test, I will be assuming that you guys know these graphs and know them well from previous algebra classes. If you don't know what the graph of 1 over x to the 4 looks like right away, look at it, draw it, make sure you remember it. As you work through the homework, there's plenty of graphing in there for you. You must draw those graphs by hand. If you do not draw those graphs by hand as you work the homework, you're gonna be screwed on the test. So you gotta practice this, okay? Promise me you'll practice this shit. The last thing I want to talk with you about today is this concept called net change. So given a function f, the net change of the function f from x equals a to x equals b is defined to be just f of b minus f of a. So you take the output associated with the input b is the larger number here, and the output associated with the number a, and you subtract them. So here, a is assumed to be less than b. This has a very intuitive understanding. Like if I want to talk about the net change in my bank account over the last month, if I end with more money than I started with, my net change is positive. My net worth has gone up. If I end with less money than I started with, my net change is negative. And to find that number, you would just take the value of my account at the end of the month minus the value of the account at the start of the month. That's like your f of b, value at the end of the month, minus f of a, value at the start of the month. It's important that you're able to do this in the context of a graph, though. So you want to be able to understand this thing not just by plugging in numbers to a formula, we want to also sort of understand a picture. So I'm going to plot some points here. We call this 1, 3, 5, 7. Why not? And we'll say that this up here, this is like that. And this down here. Okay, and I'm going to ask you a few questions about this. First, let's find the net change. And we'll do a few. Let's say from x equals 1 to x equals 7. From x equals 1 to x equals 5. And then let's answer some more qualitative questions, like net change negative, 0, or positive. From x equals 1 to x equals 3. And we'll say from maybe from, let's say from 3 to x equals 7. All right, so here's what we want to do. We want to look at this graph and answer these questions about net change. the function I graphed here on this y equals f of x. All right. So just for fun, what is f of 1?
Five.
Very good. F of 1 is 5. If you want to know what f of 1 is, you come over to 1 on the x-axis, and then you go up to the graph, and you find the y value at that point. So f of 1 is 5. F of 7 would be 3, and so on. So how do I find the net change from x equals 1 to x equals 7? What is A? What is B? What do I do?
So A is going to be, so you have to do, so the A is going to be 1 and the B is going to be 7 and it's going to be 0 because there's no net change on a graph. No, or there are. Oh yeah, sorry, there are. So it's going to be 2.
Let's go ahead and do the computation.
Because
Okay,
you
so-
have to do 5 minus 3 is going to be 2.
Right. And here's my suggestion. Take the time to write down this step, the step I just wrote in purple. Because this step is what's going to save you from having to kind of keep everything in your head. I'm going to talk about this a lot through the course, but letting the paper do some of the remembering for you is a really powerful tool. So mathematicians, we don't write steps down because we think it looks good. We write steps down to free our minds and allow us to think about the problem at hand. Instead of remembering, oh, which one is which y value, what do I need to do? I just write the thing down, and then the paper remembers it for me. For problems like this, it might seem silly, but once they get more complicated, you'll be really grateful that you've developed the habit. So, okay, f of 7 minus f of 1. Well, what is f of 7? F of 7 is 3. What is f of 1? F of 1 is 5. So this is 3 minus 5, which is negative 2. And that's a negative net change. Okay, what about from x equals 1 to x equals 5? So now A is still 1, but B is 5 now. So this would be f of 5 minus f of 1. And as silly as it might feel to write it down, it does two things on a test. One, like I said, it lets the paper remember for you, so you don't have to keep track of what goes where, what order am I subtracting, is it an x or a y value? You just write the damn thing down and it will remember it for you. The other thing is it shows me that you remember the definition, which is a really useful thing. So writing down this step, this kind of in-between step is wise. Now, even though I've been rambling, I can look back and see what I need to do. Okay, f of 5. F of 5 is 5. Minus f of 1. F of 1 is also 5. So 5 minus 5, that's a net change of 0. Why is the net change from 1 to 5 0? What is it about these points?
Because the y is the same. They lay.
That's it. That's exactly correct. These points have the same y value. They're at the same height. So what net change is really measuring is how far above or below do you end up from where you started. If you end up above where you started, then your net change is going to be positive because this y value is bigger than this y value. If you end up below where you started, you start over here, you end up over here. If you end up below where you started, then your net change is going to be negative. And if you end up at exactly the same height as where you started, then your net change is going to be 0. And again, think about your bank account. If at the end of the month I have the same amount of money in there as I had at the start of the month, my net value hasn't gone up or gone down. The change in my value is 0. If I end up with more money than I had at the start of the month, then the net change is positive. I've increased my value. And if I end up with less money than I started with, then my net value has gone down. The net change is negative. So with that in mind, is the net change from 1 to 3 positive, negative, or 0?
0.
Yeah, from 1. Oh, from 1 to 3.
Oh, sorry. What from 1 to 3 is positive.
Yeah, and notice that I don't know what f of 3 is. if I approach this like I'm going to plug into the formula and just call it a day, I'm screwed because I have no idea what f of 3 is. F of 3, I know it's bigger than like 5, but is it 6 or 7 or 6.2 or, you know, I don't know. But because this point is above this point, I can safely say that the net change is positive, even though I don't know what it is. Okay, what about from 3 to 7?
It's negative.
Good. So from here to here, I'm ending up lower down than I started. I'm starting here, I'm finishing here. This is below this. So even though, again, I couldn't compute it because I don't know what f of 3 is, I don't know what the y value is there, I can say that because this point is below this point, my overall change has been negative. Overall, I've gone down. Okay, other fun things to do are to say, can you identify an interval on which the net change would be 0? We've already seen one of those. We know that from 1 to 5, the net change would be 0. But if I looked, from like this point to like this point, the net change would also be 0. I just don't know concretely any points on the graph there. So that's it. That's net change. It's not anything terribly hard. You do need to remember the recipe. Net change from A to B is f of B minus f of A. And you do need to remember the kind of qualitative thing that if you've gone up overall, and again, it's always left to right, if you've gone up over that interval, like from 0 to 3, your net change will be positive. And if you've gone down, like from 3 to 7, then your net change will be negative. And if you're at the exact same height as when you started, at the end, then your net change is 0. Okay, we're going to use net change to build up something called an average rate of change. We'll talk about all that and the difference quotient next time. So for now, I would like you to please just work hard on that homework set that is up in WebAssign. If you get stuck on anything, you can come by my office hours, send me a Canvas message, post to the Discord, go to the tutoring and the learning commons, either in person or online. If you use the Ask My Instructor button in WebAssign, it's going to take a little while for me to get back to you. Right? I've just got like 50 different things I need to check and stay on top of. WebAssign is not my highest priority. So if you need a fast answer, don't use the Ask My Instructor button. Post something to the Discord. Just take a photo of the problem or a photo of your work, post it to the Discord. I will check that at least once a day, and then your classmates can also help you out. There's probably someone who can give you an answer right away. But that is it. Any questions for me before I let you guys go for the day? Alrighty then, so again, 2 things to take very seriously from today. Function notation. You must master function notation. There's no room for being uncertain about what f of a plus h is. And then the other thing, graphing. Make sure you get comfortable graphing the basics. As you work through the homework, please draw the graphs by hand. If you don't do that, you're hurting yourself, I swear. Life will be better for all of us if you draw those graphs by hand. If you need more time on anything, just submit an extension request. If you need help with anything, you know how to get it. Canvas, email, Discord, tutoring, or the WebAssign Ask My Instructor button. Any of those will work, but the latter is the slowest. That's it from me. Work hard on the homework, and I'll see you guys next time.
Thank you so much. Have a wonderful day.
You too.